So hello everyone. So I'm very pleased to introduce today's webinar. And during this webinar, we will get you through a journey of analyzing a router vulnerability and presenting how we leverage our time travel analysis technology. Pierre will be the one doing that. So Pierre is now a security analyst within eShard. I did this analysis with one of her colleagues, and in a very short period of time, they were able to get way over the initial assignment. So using this typical case, it will introduce our time travel analysis technology and explain how we leverage it. Initially, our time travel technology uses a full system emulation in order to provide a complete system visibility, including the kernel side. With this, any vulnerability or malware involving the kernel or multiple processes is way easier to analyze. However, in this particular case, only the userland part of the one process was interesting. So Pierre followed a very interesting path to easily set up the emulation and get right to the important part. So he will present this path in 3 steps. First, the emulation part, which is the initial step required for time travel analysis. 2, he will dig into the analysis of the vulnerability itself using our time travel technology. And the cherry on the cake, it will also get you into its exploitation. Sorry. So, Pierre, the stage is yours.
Thank you, Mark. So, hi everyone. Yeah, first and foremost, for those who are not familiar with time travel analysis, let's give a quick recap. So the idea, what is time travel analysis, time travel debugging? For those who may know our cousins on Windows, the idea is you record the entire emulation of either a system traditionally or a binary, and you record the hardware context. So you record at every single instruction executed, the CPU state, as well as any memory write or read that will happen. That way you have a visibility of the entire system. So traditionally, it requires a full system emulation for Windows, Linux, Android, and etc. You have the luxury of having both userland and kernel land. And what does it bring to the table compared with traditional debugging? Essentially, now you can answer these kind of questions that were not technically possible or hard to do in a traditional debugging environment, is move forward and backward in time during an emulation or an execution of a system. That is, for example, with a traditional debugger, if you set a breakpoint at the instruction 50, then you cannot know anymore what was the content of the memory or the context CPU at the instruction 49, because you can't go back in time. That's something you can do with time travel analysis, and that allows you to enhance your analysis of different systems. So, like I said, traditionally we had full system emulation, but the full system emulation or for full system time travel analysis, but we're pushing more and more for lightweight. So let's just try and compare the two. So what is a full system emulation? You have both advantages and disadvantages. So the first disadvantage is that you have a full system emulation. So you have both kernel land and user land, that is, the trace is quite big and etc. An advantage is that it is a full system emulation, meaning that you have both the kernel and user land. That really depends on what you're trying to do, actually. If you do not wish to analyze the interactions with the system itself, then that means you have no need for a full system emulation. It's quite costly in hardware resources for trace generation, etc. But at the same time, you see everything that happens in the system. And for the lightweight part, it's a lightweight counterpart, you have a bit more setup needed. It's not out of the box, but you can do single process emulation, which is both an advantage and disadvantage, similar to a full system emulation. However, it's quite fast because you trace way less code. So it's just a matter of choice for those who already are working with our full system time travel analysis. It will seem extremely fast at the end. However, you do not have the same level of details. It just really depends on your needs. Sometimes you do not need that much detail. So let's dive into the use case for today, now that we have that. So we were asked, what can you do with this CVE? technically, can you show us time travel analysis on this CVE? This CVE, let's just have a look at it. What's the description of this? So it is reportedly affecting a Tenda AC15 on the firmware 15.03.20-multi. It is a vulnerability in the cookie handler of the web interface, and it's supposedly in /go form /exec command. Note that there are two C's here, quite important for later. For now, we don't really care. And it affects the function within this web interface, R7 web security handler. It is a, well, common vulnerability, stack-based buffer overflow. So let's keep going. In the NIST, you also have resources, references with the vulnerability itself. And in that case, we had a GitHub repository, but weirdly enough, it's mentioning the version 15.03.18, which is different from the report vulnerability on the first main description of the NIST. If we go on that GitHub, we do still see that it is Tenda AC1518. Turns out the vulnerability is actually on the 1518 version of the router, or of the firmware rather. Let's dive a bit deeper. They mention like an analysis of this vulnerability and the detail, mentioning that a string copy is responsible for the buffer overflow, and it is populated by a function at 2b abc with a password field, and that leads to buffer overflow in the stack. So now that we know that, we also have a proof of concept to trigger that vulnerability. And like, fine enough for us, the person that asked us to look at the CVE told us maybe that can help. Qiling provides an emulation of that exact firmware, which is quite handy for us. But at the time, we did not have Qiling working on the time travel analysis. So what is Qiling? It is indeed implementing the right router for HTTPD, which is actually the web interface. And this is quite handy for us. But like I said, what is Qiling? It's really important for us to understand that, to see how we can perform time travel analysis on it. So Qiling is a lightweight emulation framework based on Unicorn, itself based on QEMU. So let's pause for a second here. QEMU emulates the hardware. Unicorn provides an emulation framework around it to manipulate a bit easily that hardware emulation. And Qiling will add a system view on top of that. That is, it will emulate system calls for us. It's not system call forwarding. It will actually emulate itself the system calls. It will also handle everything a system does usually, but it's emulating it in the context of a file system. So we'll see that. So it takes three things as a main input: a file system that needs to contain all the necessary libraries for the target executable or binary to be executed. That is, all the libraries that are going to be needed, the configuration files, and etc. It also takes the executable itself, quite simple, right? And a profile. Profile will describe different memory mappings and configurations. So that's it. That's all it takes. And the file system, actually for us, because the Tenda router is a Linux-based firmware, is rather simple. If you have the firmware, you have a Linux file system. We also, in-house, have Raven Unicorn, but let's pause for a second. What Raven Unicorn? It comes from Raven, which is our traditional time travel engine that works on full system emulation. Raven Unicorn has been built to do the same thing, but on Unicorn. And as we've seen 2 slides earlier, Qiling is based on Unicorn, so there must be something that we can cook here. And we describe in the later slides how we managed to integrate each other. But first, Raven Unicorn, as you can see on the screen, automatically records the registers of a Unicorn instance. But prior to that, we need to know the memory mappings that will Raven Unicorn needs to watch in brackets so that it can record the events in these memory regions. And you can also add custom hooks for certain syscalls and so on. So now that we know that, we have a choice to make. Either we go for our traditional full system emulation on Linux, because it's a Linux-based firmware with all its pros and cons, but we only need the vulnerabilities in a single process, really. So we could go and try and implement something with revenue core and Qiling, or like cook something around that. So the choice for us was quite simple. Let's try and enhance our knowledge on lightweight time travel analysis. So how do we set up that baby elephant, right? So we have Revenue Unicorn that allows us to do time travel analysis on Unicorn. We have the Tenda firmware file system, and Qiling has a Linux profile by default that we can tweak to make it work for us. Turns out we didn't even have to tweak it, but that's not relevant for now. But in order to do a trace on time travel analysis, we need, like we said, to record the hardware of the emulation. That is, we need to record the registers. Quite simple. Revenue Unicorn does it for us. The only thing we have to do is give it the handle to the Qiling emulation. So the way we approached the problem was, let's Qiling do the emulation and hook ourselves at the right places to record this emulation. So we simply need to give the handle to the object unicorn from Qiling to Revenue Unicorn, and we can start tracing. And now already we record the status of the different registers for every single instruction. Quite simple. But now we need to know the memory mapping, because you remember that Revenue Unicorn needs to know the memory mapping. For that, again, very simple. We have the profile, the Qiling profile that describes the stack address, the stack size, where is going to be the loader, where is going to be mmap address, is kind of where all the heap stuff is going to be stored, and so on. Quite simple. So we give it to Revenue Unicorn again. So we get the addresses of the stack, register it to Revenue Unicorn, give it the size. Here you can notice arbitrary quite big sizes. It's simply because we can't know beforehand what's going to be the necessary size. And even if we know afterhand, like in an iterative process, it doesn't really matter because it doesn't slow down as much. The emulation, you'll see it in the demonstration later. It's not needed, but the stack size, we have it, so might as well use it. That's it, right? We have the memory, we have the registers, everything is recorded. Well, not exactly. Technically, we have, as you see on the right side, the CPU, but we also have the memory, but in the middle, we don't have any disassembly. That's kind of weird. For those who are already familiar with Reven, in the GUI, in the middle, you're supposed to see your instructions go in top to bottom fashion, every single instruction executed. So that means we don't see our binary. It took us a bit of headaches, but technically what happens after digging into Qiling is that Qiling loads itself, the loader in memory. It also loads the binary itself from the file system. And then the loader will load the libraries using mmap2. But if you do remember, the system calls are emulated by Qiling. That means that our somehow our memory do not get this hook. So we need to add it ourselves. So reading the manual, we saw that Qiling provides this API POSIX system calls that we can hook ourselves into. This is how you intercept the mmap2. You just have a few conditions, because if the FD is different from OX, FFFF, so on, etc., we just simply read what has been written in the memory inside of Qiling and register it in Revenue Unicorn. Quite easy. And for the loading of the binary itself and the loader, we just had a look at the code of Qiling and readapted it for Revenue Unicorn by essentially adding this memory recording. A lot of code, but trust, it works. And ta-da! We have now our emulation that is recorded. It makes much more sense than before, right? And now that means that we can have a look at the vulnerability, emulate it, and analyze it. So we're going to analyze the vulnerability, but first, let us pause for a moment and have a look at that GUI. This is our dedicated GUI for time travel analysis. It works this way. In the middle, you have a top-down paradigm for each ever executed instruction from top to bottom. Quite simple. You see the disassembly, the addresses executed. Each instruction is called a transition in our paradigm. And you have different panels on the side that will synchronize with the selected instruction in the main view per se. So on the left-hand side, you'd have a call tree that allows you to look at the different symbols and how they interact with each other in time. You have on the right side the CPU view, that is the state of the CPU before and after the execution of the selected instruction in the middle. And you also have highlighted in yellow the different registers that are going to be impacted by that instruction. You have the memory view that is similar to the CPU's state. You can see before and after the execution of that symbol, and you can browse the entire memory. You can also have a look at the history of the access history of the selection. That is, you can see in the entire time travel trace, you can see, I say who, but what instruction affected that memory region. It is quite handy to look backward in time. How was a memory buffer constructed, for example? We'll use it in our analysis later. And in the bottom, we have a search engine that can search for symbols, can search for addresses, and so on. So now let's have a look at the vulnerability itself. We go to the last ever executed instruction because it's a vulnerability. We are showcasing a crash here. And we are popping from the stack inside of the PC, which is for those more familiar with Intel, RIP or EIP. It's actually essentially the instruction pointer. And we see that it's going rubbish. This is why we have a crash. So let's just trace back in time what's happening. We're popping from the stack. So let's have a look at that stack. And on the stack, we can see a very large buffer of A's. And we leverage the history of the access history, go back to the last time there was a write at that address, and that will allow us to see who wrote and what wrote, what caused that write at that place. Essentially, this is the last time there was a write. So we go on R0. This is the parameter that we're passing before going on to the C library. It is at this address that we have our cookie password, and the address instruction is 2F71C. Important for later, we'll see. So let's have a look at our favorite disassembler or decompiler. What happens at 2F71C? And it's a call to an scanf, which is also referencing a stack variable. So stack-based buffer overflow, we're copying some values inside of a stack and then overwriting the instruction pointer. Quite simple, but there is no string copy. If we remember, on the NIST vulnerability report, there was mention of a string copy. That's kind of weird. So turns out that no string copy was involved in that stack buffer overflow. It was an scanf. It's a mistake from the reporter. We'll see and investigate a bit that, essentially. So if we go back to that report, they were talking about function copying inside of a variable, then leading to a string copy onto the stack, causing that stack buffer overflow. So let's hunt for that function at 2BABC that's supposedly responsible for that. If we have a look at that, we found it on Ghidra, and the address is 2FEF4. So what we can do is have a look at 2FEF4 inside of our time travel engine using the search feature to search for an address, and there is 0 result. That means that this instruction was never executed. So it's the proof that we needed. There is no string copy involved. If we do a mini conclusion on the root cause, the root cause was wrong, or at least on the report that was handed to the NIST. It was an scanf responsible and not a string copy. But what would be the fun if we don't exploit it, right? So we will do a small summary of what we have with ourselves. So essentially, the stack on the binary is non-executable. That means we can forget our good old shellcode on the stack. On the router, there is ASLR, and we didn't find the leak, so it's going to be, it can be quite tricky, and there is no position independent executable, but we have time travel analysis, so we can run our exploit, see why it doesn't work, and build on that. Also, there is no ASLR on Qiling, which is quite handy. You can create your exploit before having the leak. You can have your colleague work on finding a leak while you work on the main exploit, for example. So the approach is going to be a rogue chain return-oriented programming. Essentially, because stack is non-executable, we cannot push directly our code onto the stack, so we can try and build something out of already existing code. Essentially, we just jump from existing code to existing code and try and chain that into our big trophy. But what is our trophy? Actually, can be anything, right? As long as you build your rope chain, this is why we had all these little arrows, because it's a chain. Then in our, like in real world, usually it will be a remote shell to gain control over like the router, but it could be anything really. So for us, it's going to be simply a shell. So in ARM, return are usually done in this way. You pop from the stack onto the PC, and because we control the stack with the stack buffer overflow, that means we can control the PC and we can jump wherever we want in an already existing code. So we have a small problem though, is that because we have a buffer overflow with scanf, we cannot have null bytes in our addresses, in our exploit, but the base address of HTTPD has a null byte. That means we cannot use the gadgets like from the binary itself, but we'll have to look for other gadgets, so maybe on the libraries that were involved in the emulation. So here is what we found. Chaining these three, we're able to do whatever we want. The first one simply controls R2, R3, R4, and the PC register. Second one, which is the most important one, is an arbitrary write. It's a write primitive. We write whatever we want. We write the content of R2 inside of the address pointed to by R3. And then we control a bunch of registers and the PC again. And the last one, quite important, in order, for example, to call a system function, we control R0. That means we can write a string wherever we want in memory and call, for example, the system function with that string. That is exactly what we did. Essentially, we can exploit that inside of our emulation and have a look at our exploit being run inside of the time travel. So we called with system echo the foot, and we can see our road chain being executed step by step inside of the time travel engine on the right. Quite handy. So we have a working exploit. However, on the physical router, like we said, we have the ASLR enabled. That means we need to brute force the ASLR. Why? Because we're calling, you are using gadgets from the C library, and the C library is placed at a random address memory, semi-random at least. So we need to brute force the ASLR. So we need to find the leak. But like we said, we didn't find the leak, but we are still talking about it, right? So that must be that we found something, and we found this /goform/exec command with only one C. It takes you can send a get HTTP get request to that route in the web interface of the router with CMD inputs, and it will execute a system call with as root. It's essentially very kindly let by the developer to us, which is more commonly called a backdoor. But But also, because like everything in this firmware, there is a buffer overflow here, because essentially in this firmware, every time there is a buffer involved, there is a stack buffer overflow, because everything is on the stack, or at least mostly. Kind of funny, right? So we can choose from our exploit option. We can use our very intelligently crafted return-oriented programming chain with no ASLR and pray for it to work until we find the right address, or we can simply use the feedback tool left by the developer. Well, that's quite easy. We use the feedback tool. But first, let me show you what it looks like in time travel. Oh, so on this part of the screen, we have our emulation script, and we will launch it. So we are now emulating the web interface of the router. We wait for it to be to initialize, and now we can see it's in a select loop waiting for incoming requests. So we send our vulnerability, or at least our proof of concept. We have a crash, which is quite normal, and now we can have a look at. Well, we need to re-index this trace because we just redid a new one. Raven is telling us that there is a new trace. It will regenerate everything. And as you've seen, it's quite fast, right? We've already emulated the web interface. We've already sent our exploit, and we're finishing the index of that trace as we speak. And it's on roughly 8 million instructions, which is extremely fast, considering for 8 million instructions we recorded the CPU state and the memory of every single one of these instructions. So let's do the analysis live. We go to the last ever executed instruction, which is the crash. And as we can see, we will go and watch the PC, which again goes rubbish because it takes values from the stack. We can have a look at what's on the stack, and it's indeed our very big buffer. We can go back in time and see the access history and go to the last time there was a write at that address. And it's inside of the VF scanf. We can step out of the function backwards, which means go back to the caller, which is in VSS scanf. We're still in the C library. We can go back again. We're still in the C library, which is indeed our scanf, sorry. And we go back to the R7 web security handler. We go to, which is a familiar address to F71C, which calls the scanf. So in that case, that means we can go and have a look at the first argument, which is the cookie password. We found the root cause of the vulnerability, went through the scanf to the crash, job done. About 5 clicks. So that's it really for the technical demonstration. If you have any questions, please let us know. We'll have a look at the chat.
Thank you very much, Pierre. So people can have time to write their question if they have any. So you will be able to find more details on our blog. Pierre wrote 2 articles, one about the emulation, the other part, or the second one about the vulnerability itself, and a third part will come soon about the exploitation itself. So you will get the chance to get more details and review all that Pierre explained today. And I want to give a chance also to meet us in the event where Pierre or other colleagues will go. So thank you so much. I think we don't have any questions, so we can finish the webinar today. Have a great evening or afternoon, depending on where you are in the world. And thank you so much for joining us for today's webinar.